All right, for the last video of this chapter, we're going to look at interparticle forces. So a lot of students have asked me, what in the heck do you mean by a particle? A particle could be an atom, it could be a molecule, it could be an ion, it could be one of a number of different things, it could be a metal even. It doesn't really matter. We're just talking about things being held together. And it's interesting to think about these forces that hold things together, in particular in the solid state. So let's make a note that pure solids pack into a crystal lattice. And a crystal lattice you can think of as almost like a three-dimensional brick wall, and each of the bricks is made up of one of the particles shown up above. And so pure solids pack into a crystal lattice, specifically in the solid state. So let's take a look at some example situations of various solids. And I'm just going to copy this from your book. It's one of the tables. And they did a good job of breaking these down. So in the top one, we've got sodium chloride. And the formula symbol is NaCl. This is going to be a compound because it's made up of two different types of elements, one being sodium, one being chlorine. And we know that sodium chloride is ionic, so it's going to be made up of sodium cations and chloride anions. So that's one type of situation we could run into, is just ions, right? The next one is water. Again, water is H2O, and it's going to be a compound because it's made up of different elements, hydrogen and oxygen. And it's just going to be made up of water molecules, right? Water is not ionic, so it's going to be classified as a covalent compound. Okay, and then in the next one, we've got carbon monoxide. This is just CO. Again, it's going to be a compound because it's made up of carbon and oxygen. And again, it's a covalent compound, so it's just CO molecules. And then we'll go to the next one, quartz. This is sand. It's silicon dioxide, that would be its name. And it's also a compound because it's made up of silicon and oxygen atoms. But the interesting thing is these are not molecules. So let's make a note here. This is not a molecule in the traditional sense. It's kind of weird to think about this, but silicon dioxide, when it's in quartz, is actually this big three-dimensional spider web of silicon bonded to oxygen. So it's not discrete silicon dioxide units as a molecule. It's just this big network. So it's kind of like an ionic situation where it's three-dimensional as well. All right, so not a molecule. And then down here, we've got copper metal. That's just element symbol Cu. This is just an element because it's by itself, just copper. And it's just made up of copper atoms. And then last but not least, we've got oxygen down here. That's O2. It's still an element, even though there's two oxygens, because it's only made up of oxygen atoms. And this would be made up of O2 molecules. So like I said, let's make a little note. Sorry, I just wanted to keep it clean. That this is an infinite 3D network, not discrete SiO2 molecules. It's kind of unusual. It's not something we talk a lot about in this class, but we'll talk about the formal name here in a second. But what I wanted to do first was, let's imagine we have each of these compounds or elements in the solid state, meaning they're packing into a crystal lattice up here. So if they're all in their solid state, we can imagine that we could heat them up. And as you heat them up, you could potentially rip apart the particles. So let's make a note here. So if heated, you could pull things apart and break up the lattice. Oop. This is really just a fancy way of saying we could melt things if we heat them up, right? All right, so Now the question is, how much heat? So we could actually do an experiment and figure out how much heat is needed to melt sodium chloride, how much heat is necessary to melt water, meaning ice when it's solid, how much heat is needed to melt solid carbon dioxide, how much heat is needed to melt sand, how much heat is needed to melt copper or oxygen gas. So here's the chart with all the experimental data. And I know it's kind of overwhelming to look at, but we'll just try to focus in on the melting, because honestly, that's the most interesting part, is going from the solid state into the liquid state. So we can see oxygen melts all the way down at negative 218 degrees Celsius. It requires very, very, very little heat to melt oxygen, which is why we almost never encounter solid oxygen in our day-to-day lives. It's always gas, right? Because most of the time we're dealing with it, it's above 0 degrees Celsius. Okay, or I should say it's above negative 183 degrees Celsius. Okay, so oxygen melts at a really, 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 really low temperature. Let's go to carbon monoxide. It melts at a little bit higher temperature, but still really, really low. Water melts at 0 degrees Celsius, right? So that makes sense. We talked about that earlier. Salt, NaCl, melts all the way at 801 degrees Celsius, so far hotter than your oven could ever get up to. You would actually have to have a special furnace to do this. Copper, kind of same idea. In order to melt copper, you're going to have to crank up the temperature even higher. And then last but not least, quartz, meaning sand, requires an insanely high temperature to melt. That's why you have to have special equipment to make glass. You can't just put it in a generic oven and melt sand and make glass at home. So as you can see, if we look at this, it requires more and more energy. So let's make a note. It takes more energy to melt. All right. And you might be thinking, well, what about the other ones? What about boiling? Let's just focus on the melting one, because there's actually some outliers with boiling that we're just not going to talk about. So let's focus just on this generic trend. So oxygen takes very little energy to rip apart oxygen molecules. Carbon monoxide molecules takes a little bit more energy to rip them apart. Water molecules, even more energy than carbon monoxide. Salt particles, meaning the sodium and chloride, even more energy. Copper atoms takes even more energy to rip apart from one another. And then quartz, we said that's made up of that three-dimensional network of silicon and oxygen atoms, takes even more energy to rip them apart. So let's kind of make a little flowchart here. So we'll do most energy needed right here. So this is going to be energy on this scale. All right, and then we'll work our way down to the least. And then over here, I'll just write compound. CMPD is just the abbreviation for compound. And we said that silicon dioxide is going to be at the top, right? So we've got silicon dioxide as taking the most energy. Now the question is, what force holds together the particles? All right, and if we look at silicon dioxide, I'm just going to quickly show you a picture and then erase it, but silicon dioxide's kind of funky. So silicon dioxide, like I said, is one silicon atom bonded through a three-dimensional network to a bunch of oxygen atoms. And you can imagine over here we'd have another silicon bonded to a bunch of oxygens, and goes on and on and on and on. So what this is called is a network solid. It's a unique type of covalent bond. So let's make a note here. So network solid. And this is going to be one of our new terms, so I'm just going to highlight it. But a network solids basically is saying that the lattice sites are occupied by atoms covalently bonded to each other in a 3D, sometimes 2D network. And these are not discrete molecules, meaning there's not going to be little SiO2 molecules floating around in space. It's just a big three-dimensional spider web of silicon and oxygen. So it takes a lot of energy to rip apart all of these covalent bonds holding together these particles, right? So in order to rip these apart, we would have to break covalent bonds. And not just one covalent bond, we'd have to rip apart a ton of covalent bonds. So it would take a lot of energy. All right, let's do the next one. The next one in that list was copper, so Cu. So now the question is, what force holds together the particles of copper in the crystal lattice? And this is actually called a metallic bond. And this makes sense because copper is a metal, right? So I'm going to highlight this as a new term. And a metallic bond is kind of interesting. It's essentially a bunch of metal kernels, which are nuclei with a positive charge, surrounded by a sea of electrons. So metals are kind of weird. If you remember, I said one of the characteristics of a metal is they're really good electrical conductors. And that has to do with the fact that they're basically sharing electrons with one another in this big three-dimensional network. So metallic bonds are pretty strong. It takes more energy to rip apart metal typically than it does to rip apart just discrete molecules like O2. Okay, let's do the next one. So the next one is NaCl. And NaCl, if we think about it, is an ionic bond. And we have already talked about these ionic bonds, if you recall, are just the attractive force between cations and anions. Okay, so the positively charged sodium is going to be attracted to the negatively charged chlorine, and they don't want to let go of one another because they complement each other. So it takes a fair amount of energy to rip them apart. Okay, so we've gone through those. Those are the really high energy ones. Now let's go to water. All right, so water is a weird one. Water, if we look at it in a crystal lattice, actually tends to kind of pack almost like a network solid, almost. However, it's not completely covalently bonded, meaning there are discrete water molecules. They just tend to interact strongly with other water molecules. So this is called hydrogen bonding. And hydrogen bonding is pretty unique. It's a really strong dipole force, so it's similar to dipole forces, which we'll talk about next, but occurs with molecules where hydrogen, I'll just say where H, is bonded to either fluorine, oxygen, or nitrogen. So the way I always teach my students this is I ask them, is H on the phone? If you have a hydrogen directly attached to a fluorine, oxygen, or nitrogen, then that hydrogen can participate in hydrogen bonding. The way I kind of describe this to people is that hydrogen will act as a bridge to another atom. It essentially will be held by both atoms, one through a true covalent one through a true covalent bond to the other atom through a hydrogen bond. All right, so in this case, This hydrogen is bonded to oxygen. That means that these really, really stick to one another. All the water molecules stick to one another through this network of hydrogen bonding. All right, so that's kind of interesting. And then we go to CO next. This is different. This is just called dipolar force. We don't have any hydrogens, so we can't hydrogen bond. And a dipolar force is the attractive force between the electron-rich end of one molecule and the electron-poor end of another. And so if you remember, an electron-poor side of a molecule can be indicated with delta plus. So the delta plus of one molecule is attracted to the delta minus of another molecule. So it's not as strong as ionic because these are just partial charges, meaning they're not true ions. They're just kind of unhappy because some other element is stealing electrons from them in this case. Or in this case, this element would be happy because it's stealing electrons from somebody else. All right, so we're almost done. The last one we've got to do is going to be O2. And O2 is kind of unique, right? If we were to draw the Lewis structure, there's going to be no net dipole at all. So there's still a force holding them together. This is called dispersion forces. And a dispersion force is what is called a fleeting dipole. Because electrons can't be everywhere at once. Whoops. So another way of thinking about this is if you're an electron and you take a snapshot with a pretend camera, right? That electron has some probability of being on one side of the O2 molecule or the other side, basically creating an instantaneous dipole, but not a permanent dipole. So it's not a very strong force, but I did want to make a note that this increases with surface area. So we have to also think of this as being a relatively strong force if we have a molecule with a huge amount of surface area. All right, the interesting thing is if we look at all of these, right? All of these have dispersion forces in them, meaning there's also the probability of an electron just being at one side of a molecule and not the other during a snapshot in time. However, it's really weak in CO and it's really weak in H2O. Therefore, typically when we're asking questions about these, we say, what is the primary force holding together the particles? Meaning, what is the strongest force? Not what is the weakest force. We want to know the strongest one. That tells us a lot more information. All right, I hope that makes sense. I know this is a little bit confusing, but let's go ahead and move on to the new section. And, oh yeah, before we do that, I wanted to show you this other thing. Sorry, I was getting a little sidetracked. And this is something that bugs a lot of students, is they think the order I listed it is absolute. And I just wanted to show you this. Note that the forces vary in strength. So what I mean by that is we can see the increasing strength on the top in this chart. So typically covalent bonds in a network solid like diamond have a huge amount of strength. However, there's a range, right? So it's saying it could fall anywhere in this range. Same thing with metallic bonds. So there may be some metallic bonds that are stronger than some network solids. Same thing with ionic bonds. There's going to be a range. Same thing with hydrogen bonds. Same thing with dipolar forces. And then same thing with dispersion forces. So these aren't absolute. In particular, in this top section, there's a lot of overlap. Meaning this is not an absolute ranking. All right, so let's finish up with something kind of fun. And I apologize, I know this video is going long, but I wanted to focus in on water. Water is weird is going to be my last section here. And let me talk about the weird properties of water. So I'll do example number 1. And this is more of a thought experiment. So let's imagine that you heat a gas. All right, so if you heat, let's say, the gas on the inside of a hot air balloon, you're going to make that gas less dense, right? That's why hot air balloons float. Conversely, if you cool a gas, you can make it more dense, right? This is true for just about any gas on our planet, right? However, let's take this situation. So let's say you cool water into ice, right? So if we look at it, I'd say, well, we're cooling. Wouldn't we expect this to be more dense? So let's imagine you cool water in your ice cube tray and form ice, and then you put that ice back into liquid water. Will the ice sink or float? That should float, right? So it's not getting more dense, it's actually getting less dense. And then the question is, well, why? Why would water do this? Water is kind of unique. It's one of the only molecules that does this. And it does this to allow for better H bonding. And I remember learning about this in general chemistry and thinking, great, that's cool. It's just an odd example. But then I took an ecology class where we talked about this more. And my ecology teacher was obsessed with water. And he said, no, you don't understand how important it is that ice is less dense than water. You don't get it, do you? And I was like, well, can you explain it? He said, well, let's imagine that ice sinks, right? So if ice were more dense than liquid water and sank into the bottom of the ocean, what would our ice caps look like? Well, they wouldn't be ice caps, right? Instead, all of the ice would sink on the bottom of the ocean and we'd have ocean water on top. Well, what would that do? Well, ocean water is a darker color than ice, right? So if it's a darker color, it would absorb more sunlight. And if it absorbs more sunlight, that means our planet's going to warm up. If our planet warms up, it get hotter and hotter and hotter and hotter and hotter, and we basically be a very, very hot planet to the point where we can have any life on it. So the fact that ice floats is super important to our very existence. All right, let's do one last example. Again, another weird one. So this is example number 2 of how water is weird. And what I want to do is I want to do a bunch of analogous compounds that are in the same group. So I'm going to do H2TE. So dihydrogen telluride, I guess. And then H2SE. And then H2S. And then we'll do H2O on top. But you see how all of these are all in group 6A on the periodic table. All right, well, we could look up the boiling points for all of these. So let's start at the bottom. At the bottom, this would boil at negative 2.2 degrees Celsius. We make this a big C. And then as we move up, we actually get more negative. It's negative 41.3 degrees Celsius. And then next, we're going to be at negative 60.3 degrees Celsius. And then we would expect this to be more negative. So the question is, well, what is the actual boiling point of water? Well, we know that it's 100 degrees Celsius. It's not negative 100 degrees Celsius, which is what we might expect. It's positive 100 degrees Celsius. So then the question is, well, why? Why would this have a higher boiling point? Well, it's due to H bonding. It's the hydrogen bonding feature we talked about. The fact is that this hydrogen is bonded to oxygen, so it follows that H on the phone rule, where this one down here can't H bond. Same thing with all of these. So the fact that the hydrogens and water can H bond changes the properties and does all these weird things like affecting density, affecting boiling point, all this stuff. But it's really unique. It's something I didn't really appreciate when I was starting out in chemistry, so I thought I'd share it with you. All right, good luck studying, and let me know if you have any questions.